Hello everyone, and today I'll walk you through one of the most fascinating world of distributed systems. So, what are distributed systems? They are like invisible backbone behind your big tech platforms like uh, Amazon, Google, Meta, Facebook, everything. And understanding their design is critical for building scalable, reliable, and high performance applications. So let's see what exactly is a distributed system. So distributed system is a network of independent computers appear as a single cohesive system. So what does this mean? So distributed systems are like individual servers or individual computers which are running as a single computer. It appears to be running as a single computer. So these computers coordinate through each other by passing some messages over the network. How they will pass the network and what are the different forms of communication we will see in the upcoming slides. Why do we need distributed systems? For scalability. It can handle hundreds of millions of users concurrently. Fault tolerance. They are designed to survive hardware and software failures. So top tier systems can achieve like 99.9% of uptime. So less than 5 minutes downtime per year. So it means the downtime is like almost negligible. High availability. Services can be distributed across the globe, allowing users to access them anytime, anywhere with low latency. But latency can be a problem in distributed system if not handled correctly. So how to handle those? Let's see in the upcoming slides. Let's look at some real world systems that we all use in our daily lives. We all have used WhatsApp, Google Drive, Amazon, right? WhatsApp processes over 100 billion messages daily and it uses Erlang distributed systems. Same as Google Drive stores more than 2 billion files powered by GFS distributed architecture, and same as Amazon also, and many other big tech companies like Netflix, Instagram, all uses the same distributed system architecture. And the main reason why we all use these services in our daily life is probably because of the distributed architecture they use behind the scenes. Let's understand in depth what a distributed systems are. Like what distributed systems are made up of. Why do we call it a distributed systems? We have something called nodes. Nodes can be a physical machine, it can be virtual machine, it can be containers, serverless functions, it can be anything. Just nodes are just computers, independent computers, and they communicate each other through some messaging protocols like REST, RPC, gRPC, and Kafka for message queuing. So here's a diagram of how distributed systems are built at its core. These are nodes, node A, node B, C, and so on. So these nodes are nothing but servers or just computers connected through each other. Like as we discussed in this slide, they communicate through various communication protocols. So node A sends some data to node B, which is another server connected to A, and the node B takes the data and forwards it to node C. And node C, let's say, gives half of the work to node D and half of the work to node E. And after completing the task given to node D, it will return its results. And after completing the work which is given for node E, it also returns to node C. And after getting the result from node D and node E, what C will do is it will combine all those results and again sends back as a response to node B, and again same the node B also responds to node A. So by doing all these, we are not reliant on a single server, we are reliant on multiple servers, so that if one server fails, another can do its job. Let's say node E fails, so we have node D, node C, and many more nodes to to work as a backup server for node E. This is main reason why distributed systems are used everywhere. But communication between these is not easy. We deal with some unpredicted network latencies, dropped messages, and varying bandwidth, especially when these systems or servers are distributed all around the world. We just saw that these servers are distributed all around the globe. So, to make the system feel like a single unit to user, there might be many complexities at the back end of these servers. But distributed systems aim to hide their complexities through several transparency properties. Let's see them. A user should access resources the same way whether they are local or remote. So what does this means? As I said earlier, a system or a server can be located anywhere. Let's say in the previous slide there is a node A. These nodes are nothing but servers. So node A can be located in, let's say, Mumbai, and node B can be located in somewhere in Sydney, and node C can anywhere located in any parts of America. So a user should access resources the same way whether they are close to the server or away from server. It doesn't matter. The user should experience the same. Location transparency, it's also the same. Users don't need to know where the data physically lies. So user should not know where the data is coming from. It should feel like one integrated system. Failure transparency, if a server goes down, the system should recover without the user noticing, often within milliseconds. If a server fails in any continent, the end user should not be aware of that. The end user should experience in uninterrupted service. So that's why the failure transparency goals has to be met. Concurrency transparency, multiple users should be able to interact with the same system simultaneously without conflict, like how we all binge watch Netflix without being interrupted. So the same way every user should experience. So these features are critical to making distributed systems usable, scalable, and user friendly. Now let's talk about the famous and the most important CAP theorem. So what is CAP? CAP is consistency, availability, and partition tolerance. It states that in any distributed system, you can only achieve 2 out of 3 guarantees at the same time. What are the 3 guarantees? The consistency, availability, and partition tolerance. What is consistency? All clients see the same data. Every user should be shown the same consistent data. What is availability? Every request gets a response, even during failure. Partition tolerance operates despite network splits. What does that mean? A system continues working even if some nodes or network segment fails. Let's now discuss some architectural models. There are mainly three models: client server architecture, client server model, peer to peer model, and microservices model or architecture. Let's see the client server architecture. in details in our diagram. So in a client server model, many clients send requests to a single centralized server, and the server responds back to every single client. But there is only a single server responding to every client. But in the in peer-to-peer architecture or peer-to-peer model, we have multiple nodes. So if, let's say, if this server fails, then there are multiple other servers to keep the whole system running. So this will not crash the whole system, and there will not be any downtime. So that is one of the main advantages of distributed systems. Let's see microservices architecture a bit later after understanding some concepts, because microservices architecture are one of the most important and widely used architecture all around the world. Now let's look at how distributed systems are structured internally. The layered architecture. There are 5 layers: presentation layer, application layer, data layer, network layer, and infrastructure layer. Let's see them one by one. So, presentation layer, user interface and client side logic. It is what the user sees and interacts with, like websites or mobile applications. Application layer, business logic and API orchestration. It contains business logic and service rules. Data layer, it contains databases, caching, and storage. Network layer, so network layer manages traffic with load balancers and API gateways. Infrastructure layer, all the infrastructure parts like deploying your applications on cloud platforms, and containerizing your applications using Docker, and deploying it using Kubernetes, using virtual machines. All these come under infrastructure layer. The whole DevOps part comes under the infrastructure layer. Let's understand these layers in depth from a diagram. Presentation layer is the user interface. The user sends a request which goes through application layer, where the business logic is handled and the servers are connected to the database and other communication protocols. Now let's see how microservices architecture is built. Microservices architecture is built using the basic concepts of distributed systems. So in microservices architecture, there are many servers, like as you can see here, there is a service called auth service, and a user service, and order service, and many more. It can consist of as many as it can be. Netflix uses more than 700 microservices. This is a single microservice, this is a single microservice, so this uses 5 microservices. Same as this, Netflix uses 700 microservices. Microservices is nothing but just, instead of single server handling all the work, there are multiple servers to handle multiple tasks. So this is a server which will be handling auth part of the authorization part of the application. This is a server which handles user functionalities like login, logout, and user related things. So in this manner, every different tasks are assigned to different servers. When a client or a user requests something through the API gateway, the request gets distributed according to their respective tasks. Like authorize, if the client or user tries to log in or log out, those works are handled by this service. And if the client or user tries to make a payment, the request is handled by this microservice. In these type of architectures, the client and the server will be connected through a gateway, and they can be connected in various forms of communication protocols, like example REST APIs, gRPC, and even WebSockets. In microservices, there is a concept called event driven architecture, where we use a message queue in between two servers. So what is a message queue? Message queue is nothing but it's literally just a queue. Let's assume a user orders something and the order service sends the request to the payment service, and the payment will be successful or failure. But what if three users orders something at same time, or one after the other? The order service will push three requests at same time to the payment service. In that case, payment service might fail. So in that case, message queues plays an important role, where order service pushes all the requests to the message queue. There is a queue, and the message queue pushes the requests one after the other to the payment service. So in case of a payment service failure, the data will not be lost. The data will be stored in the message queue, and once the payment service gets recovered, again the message queue will push the request to the payment service. Hence, there will be less downtime and less failures. So, the first challenge is latency. As we saw here, in such a complicated microservice architecture, where one services communicates to another and that service communicates to another, so in these kinds of architecture, latency is one of the common issues. So, to tackle those, we can use CDNs, caching, and even some faster protocols. Like, for example, gRPC communication protocol is faster than REST. So, we can optimize the latency by using more gRPC than REST wherever possible. The second problem is partial failures. Here, let's take an example. If the payment services fail, these payment services should be back running as soon as possible. So that is the whole point of this distributed systems, right? If a service fails, if a server fails, it can individually be upgraded so that it will be running again. To make sure that a failed service will be working again, we can use some techniques, or like implement retries, timeouts, and circuit breakers to gradually recover the failed services. So the third problem is data consistency. Let's see how. In this example, the auth service is connected to a database, the user service is connected to a database, and the order service is also connected to a database, and many other services will be connected to a same, it not necessarily a same database, but a different database. Let's take an example. If a user changes his username or email ID, the auth service will be handling the part. So whenever the user changes username, the the auth service which is connected to the database will be updated with the new username. But the user service, order service, payments, inventory, all these services will be storing the old username. So the new username will not be updated in any of these databases. To tackle this problem, we can use some mechanisms like quorum mechanisms and CRDC tools, and some general backend data handling. So the final challenge is security. So security will definitely be a problem, because we will be managing many services, and ensuring data security across all those services and all the databases connected to those services will definitely be a major task. To ensure security, we can uh, follow some best practices, like encrypting data, not only passwords, Passwords will be, however, encrypted, but all the data that will be stored in the database can be encrypted. And furthermore, we can use best practices like token based or session based authorization, role based authentications, and implement some good cybersecurity practices. At the end, to summarize everything that we have seen in this video seminar, I will be summarizing everything. Distributed systems offer scalability, reliability, and enhanced performance. Understanding the CAP theorem and its inherent trade offs is crucial for designing. Key challenges includes managing partial failures and ensuring data consistency. And you have also seen many real world examples that we all have discussed in the initial part of this video. And I hope this helped you guys to appreciate the uh, beauty of the complexity behind the distributed systems. Thank you.